Okay. So we were talking about differentiation, right? In the early session, actually, we talked about tangents and the derivative at the point. The derivative is a function, and I have already recorded, okay, and also shared the link. Actually, that is the playlist, and all the videos that we are going to have here will be uploaded there. Okay, anytime. I mean, at least what topics we have studied and what are you expected to do, we can learn from that playlist. And also with your TAs, okay, and also they will continue teaching online, all right? You are going to meet them maybe twice or three times a week. And especially this one is for discussion purpose. If you have any questions, you can bring them and discuss together also here. Or if you have nothing to discuss, then I will just solve a few problems related to these topics, okay? So now here we will talk about differentiation rules. Okay, that is enough for today. In our next meeting, maybe tomorrow or Friday, we will talk about 3.4 and the 3.5. So now, as I have just told you, every time calculating the derivative of a function using, what is it, the definition, it is very tedious. It takes a lot of time. Maybe for simple functions it's fine, but some complicated functions, it takes a lot of time. And that's why using definition for every time, it's not a good idea. So now we are going to generate some formula to calculate the derivative of some functions. Okay. The first one, if f has the constant value, that means f is a constant function, then derivative of this function is equal to 0. Okay, and using this definition, we can prove this. Why is it so? Our function is c, right? And that f prime of c here, f prime of c, again, using the definition here, we have limits, and as h approaches 0, right? And the value of the function at x plus or c plus h is all, I mean, its value is always the same. So here we have c minus c over h, that is equal to 0, because 0 over h is equal to 0. Limit of 0 function, that's equal to 0. That's why if you just differentiate any constant function, its derivative is equal to 0, right? For example, let's say our function is f of x is equal to 5, for example. What is f prime of x? That's equal to 0. Another one, power rule for positive integers. If n is a positive integer, then if you differentiate this x to the power of n, that's equal to n times x to the power n minus 1, right? And maybe you are familiar with this formula, but again, how? Why is it so? I'm just going to use one thing here. Number one, to calculate this derivative, I'm going to use another form. That is here, suppose that actually here we are talking about this function, f of x is equal to x to the power of n. Here, n is, let's say, positive integer, right? And I'm going to use this formula, f prime of x. If you remember, we have alternative form, that is limit as not h. Here, when z approaches 0, a 0, x, here we have f of z minus f of x over z minus x, right? And also it gives us the derivative of the function at x. And another thing you have to know here is, what is this? Here we have z to the power of n minus x to the power of n, right? And we can always actually factorize this. How? We can factorize it as z minus x, and here we have z to the power of n minus 1, and it is minus, it is plus. Here we have z to the power of n minus 2 times x plus z to the power of n minus 3 times x squared dot dot. It continues here, and here we have x to the power of n minus 1. And if you just notice here, the sum of the powers here is n minus 1. Here it is n minus 1. Here we have n. If you just add this n minus 1, right? Now, if I just divide this by z minus x, if you divide this the whole thing by z minus x, right? What do we have here? Then all these two things cancel each other, and also that thing is left, right? So using this, now what happens if limits z approach x then? Then here we have z to the power of n minus x to the power of n over z minus x. Now z is approaching x, right? Also, it gives us the derivative of the function at x. So that thing is equal to the above, this expression, right? And when z approaches x, the z to the power n minus 1, it approaches x to the power n minus 1, plus this one again, here we have x to the power of n minus 2, x squared, which is equal to x to the power of n minus 1, and dot dot, the last thing, also x to the power of n minus 1. And how many terms do we have here? N terms, right? Starting from here, n minus 1, 1, because here 1, 2, 3, blah, blah, blah. And the last one is x to the power of, or z to the power of n minus n. That's why here we have z to the power of n minus n, starting from 1 until n. So if you just simplify this, here we have n times x to the power of n minus 1. Okay, in general also it is true for every real number, but for real number part we will prove this later in chapter, maybe chapter 7. In general, if n is any real number, then the derivative of x to the power n is equal to n times x to the power of n minus 1. Some examples: for example, f of x is equal to x cubed, right? What is f prime of x? F prime of x is equal to 3x squared, right? Another example, how about f of x is equal to cube root of x? Okay, so which means that I can write it as x to the power of 1 over 3. Then what is f prime of x? F prime of x, this 1 over 3 comes to the front, 1 over 3. Here we have x to the power of 1 over 3 minus 1, which is equal to 1 over 3, x to the power of minus 2 over 3, right? And how about another example? Let's say g of x is equal to square root of x to the power of, for example, let's say, what is it? 2 plus pi. Okay. And again, I can just write it as in the index form, right? We can just write it as x to the power of 2 plus pi over 2. Then what is g prime of x? If you differentiate this, actually, the power comes to the front. Here we have 2 plus pi over 2, it's just a constant number, times x to the power of 2 plus pi over 2 minus 1. Okay. And derivative constant multiple rule. Okay, here we have a function u is a function of x, and if you just multiply by c, that means I can just take this c out and evaluate this. Again, we are just using the limit property, right? And because this cu, right? Again, how do you calculate this one? If you just equal here this d cu over dx, right? And by the definition, that's just equal to limits as h approach 0, right? Here we have f, actually, what is it? Our function is, let's say, c times u x plus h minus our function c times u. Here we have cu, and over here we have h. Now, as you see here, c is a common factor. Using the property of limit, we can take this out. So I can write it as c times limit as h approach 0. Here we have u of x plus h minus u of x over h, right? Which is equal to c times u prime of x. Okay, let's continue. One example for this example. Okay. For example, suppose that our function is something like this. Here we have 3 times x to the power of, what is it? For example, let's say, not x, let's say x squared minus 2x. Okay. So how do you differentiate this? Then f prime of x, and the whole thing is multiplied by 3. I can just keep this 3 here and differentiate this function. And the derivative of x squared, that's equal to 2x. Derivative of 2x, that's equal to 2. So now I can simplify this, take this 2 out. So that's equal to 6 times x minus 1. All right. In a similar way, but I will just skip this. If u and v are differentiable functions of x, then the sum u plus v is differentiable at every point where u and v are both differentiable. At such points, the derivative of the sum of the two functions is equal to the sum of the derivative of these functions. Right? For example, again, suppose that I'm given, let's say, f of x. Okay, so let's say that is 2 times x to the power of 7. Let's say it is minus 1 over 2 times x to the power of pi plus 1. Okay, so as you see here, it's just the sum of two functions. Suppose that, let me just denote this by function u, and this one by function v. Okay, so now from here to differentiate this f is saying that just differentiate this u. Okay, let me just take the whole thing as v, including this minus, and differentiate v and just add them up. So what is u prime of x? And this 7 comes to the front. 2 times 7 is 14, x to the power of 6. And how about v prime of x? Here we have minus 1 over 2 times pi plus 1 comes to the front. It is pi plus 1. And x to the power of pi plus 1 minus 1, that's equal to pi. Now from here, then f prime of x should be equal to, what is it? It is u plus vx. Using this property, is just equal to u prime plus v prime, which is equal to, what is u prime? It is 14x to the power of 6. X must be the same. Let's just write here x. And what is v prime? That is minus 1 over 2 times pi plus 1 times x to the power of pi. Okay, Stephen, solve. Is everything okay? Stephen, are you there? Mr. Steven, I think she's already sleeping there. Okay, let's not wake him up.
I don't see his name, so he might be not joining.
Yeah, Steven is there. I can see his name. That's why I'm calling him.
Oh, he's chatting.
Yes, I cannot open the mic. Okay. Okay, Steven, if you can hear me, all right. Pulpin, how about you? Can you hear me, Pulpin?
Yeah, I could hear fine, sir.
Pulpin, where are you? In Phnom Penh?
Yes, I'm at home.
Okay. You're at home. You have coffee at your table?
No, but I have a lime juice.
Oh, that's also good. That's also good lime juice. Okay. Let's continue. Okay. Now here, why am I doing these things? Okay, just to give some intuition about these derivatives. Okay, and after that, practicing questions, that's not so hard. Maybe after this lesson, we will do maybe one extra problem solving session. I will give you more examples. Here in this property, okay, it says that if u and v are differentiable functions of x, then so is their product uv, and the product of u times v is just equal to v times u prime, right? In prime notation, what is this? That is v times u prime plus u times v prime. Okay, so again, why is it so? And we are going to use this a lot, actually. That's very important, one of the important properties. And y is equal to this. Okay, so I'm going to prove that this d dx, okay, uv, both are the functions of x. By definition, how to calculate this? That's equal to limit, right, as h approaches 0, And here we have u, we need to give an increment. That means that here we have u x plus h times v x plus h minus then v of x. Actually, first I need to write u. Okay, that is u. And here we have vx over, okay, here I have h. I mean, calculate the derivative of this one using definition means this. I'm just using definition, right? Here we have f of x plus h minus f of x over h. So here our f is u times v, the product of two functions. Okay. So now, how do we evaluate this? Here it says that u and v are differentiable. That means that the limits are given. Okay. So I'm just going to write this in that form. So that's equal to limit as h approaches 0. And just for now, I will keep this h outside. Okay, let me just keep it here. All right. So here we have u x plus h times v x plus h. Okay. So I just add and subtract something because I'm just going to write this actually in that form. I mean, where it gives us the derivative of u and derivative of v. Okay. So if I just add here, what is it? Minus, okay, I multiply this by this, u of x times v of x plus h. And also add this, u of x times v of x plus h. But still I have here, what is it? Minus u of x times v of x. Okay, I just did very simple algebraic manipulation. I just added something and subtracted something. But here we have actually u times v. Now equals limit as h approaches 0. Here we have 1 over h. Okay, so here v, it's a common factor. So I can just write it as u x plus h minus u of x, right? And here times, here we have v times v of x plus h. How about the second part in these two things, right? What is a common factor? U is a common factor. Take this u out. So plus, here we have u of x times, here we have v of x plus h minus v of x, right? Actually, now I can just write this 1 over h here. I can just write it here because it's just a common denominator. And also I can just write this one here. Okay. Now, as you see here, this one actually, this part, what is it? U of x plus h minus u over h. As h approaches 0, it just gives us u prime of x times, how about this thing, v of x plus h? When h approaches 0, this approaches v of x. Plus, here again, u of x, it's not dependent on h. So with respect to x, it's just a constant function, that is u of x. Times, how about v of x plus h minus v over h? It gives us v prime of x, which is the formula u prime v plus u v prime. So the product of, the derivative of the product of two functions is equal to like v times u prime plus u times v prime. Okay, before I continue, let's just see a few examples, then we will move to the next one. Okay, so, all right. All right, example. Okay, what kind of examples? Okay, just a minute. Let me see some examples from the book. At least I want to show me 1 or 2 examples, then we will continue. So in chapter 3, so okay. All right, one example from the exercise 3.3. Yeah, unfortunately, I didn't prepare this earlier. Anyway, suppose that we need to differentiate this function. Y is equal to 3 minus x squared times x cubed minus x plus 1. Okay. So one way is I can just expand this and differentiate this. Another way is suppose that let me just label this by function u, this part by v. Okay, now what we have here then? Our y function becomes just u times v, right? Now from here, what is y prime is just equal to u prime times v plus u times v prime, right? Now what is u prime? U prime is 3 minus x squared prime. And the derivative of 3 is equal to 0 minus x squared, that's equal to minus 2x. And how about v prime? V prime is x cubed minus x plus 1. And here we have prime, that's equal to 3x squared and then minus 1. So now if I substitute here equals u prime minus 2x times, and here we have v equals x cubed minus x plus 1. Here we have plus v prime, that's equal to 3x squared minus 1. And after that, we have u. What is u? 3 minus x squared. Okay. But of course, sometimes if we just expand this and differentiate, maybe it will be much faster. Okay. But still, sometimes you cannot do that. We have to just differentiate in this way. Especially, for example, our u is trigonometric function, v is some different function. Actually, if you expand this, it gets very complicated. All right. All right, that's just one example using that property. How about that thing? If u and v are differentiable at x and v is not equal to 0, then the quotient u over v is equal to u prime v minus u v prime. Okay. So now using the actual definition, again, we can calculate this, but I'm going to use the previous property. Okay, because now u over v, I have to evaluate this one, the derivative of these two functions, why the quotient of these two functions. Actually, I can just write it as u dot v to the power of minus 1. And here we have prime. Okay, now it just becomes the product of two functions here. So which is equal to u prime times v to the power of negative 1 plus u times v to the power of negative 1 prime. Okay. So with this part, we have no problem. For the first part, it's just v to the power of minus 1. It's just equal to u prime over v. The second one is u dot v to the power of negative 1 prime. So how do we calculate this? V negative 1 to the power of, let's say, the prime. Again, here, actually, what is it? It is just the power is negative 1. So the negative 1 comes to the front. So it is negative 1 times. Now we should subtract here 1 minus 1 minus 1. That is minus 2, right? Okay. So that's it. That's equal to, what is it? Okay. But actually, it's a composite function. If I do like this, at that time, I need to write here v prime also. Anyway, so that's equal to minus v prime over v squared. Okay. So because what I'm doing here is just differentiating a composite function, all right, and just how to remember that thing. And after that, if you substitute there, here we have u prime over v plus u times, what is v to the power of negative 1 prime? That's equal to minus v prime over v squared, which is equal to, now common denominator is v squared. And also I should multiply the first numerator by v. So here we have v times u prime. Here we have minus u times v prime. All right. So second and higher order derivatives. Okay, in this way, actually, also second order, third order, fourth order, we can differentiate more and more and more, maybe depending on the problem. Because, for example, if you in our next subchapter, we will talk about what it is about the derivative as a rate of change at the time if our function is position function. If you differentiate one time, it gives us velocity function. And if you differentiate twice, it gives us acceleration function. If you differentiate one more time, that means three times, it gives us the jerk function. Okay. That much is enough for today. Okay. Again, I'm going to share this, and tomorrow also we're going to have class. Maybe on Friday we will solve more. We will solve more questions. All right. Thank you very much. See you tomorrow. Bye bye.
Goodbye, sir.
Thank you.
Bye,
Bye
sir.
bye. Bye.